will have x is x, y is y, and z is g of x, y. So in this case, actually, you can compute this cross product. And this has been done. I did it in class. I wrote this formula in class. The computation is explained in the book. You must have done it many times for homework. So you might as well just remember the formula. And the formula is like this. It's minus gg dx minus dg dy. So this is I, this is j, plus k, if I remember correctly. Please correct me if I'm wrong. I think it's correct. This formula you just get by applying that general formula in this particular case. It's just that when you compute the cross product, so you have to compute this, the determinant of a 3 by 3 matrix. It's just that the matrix becomes very simple and it simplifies, so it's easy to compute. I'm sorry? That's right. I did not close the parentheses, for which I apologize. Okay. No, please tell me, because we want our worldwide audience to see only the correct formulas. So, okay. And now, if you have this, you can compute its magnitude very easily. And so it's just going to be the square root of the sum of squares of these components. So it's like this. Okay. So we actually have not just the magnitude, but we actually have a formula for the cross product, which I will use in a minute. Okay. So that's the first special case. There is a second special case when your surface is part of a sphere. The second special case is M is part of a sphere of some radius. Let's call this radius R. So this radius R is just a number. So you got a sphere which is of this radius, and your M could be just the entire sphere. Could be the entire sphere. Okay? Or it could be a hemisphere. Or it could be part of a sphere which is confined within a cone. It's like an ice cream cone, right? And that's just the surface of the ice cream. So in each of these cases, a good way to parameterize such surface is to use spherical coordinates. Spherical coordinates we learned before. Spherical coordinates give us an alternative coordinate system for the entire three-dimensional space. And we've got three coordinates. We've got rho, phi, and theta. But now we are on a sphere. We are on a sphere of radius r. So from the point of view of spherical coordinates, this coordinate rho is fixed. Rho, the coordinate of the spherical coordinates, is equal to r. Right? But we still have two remaining spherical coordinates which we can use to parameterize our surface. Which is good because the surface is two-dimensional, so it requires two independent coordinates. And phi and theta give us these two coordinates. So in other words, u and v here are phi and theta. For example, if it's the entire sphere, you will have theta going from 0 to 2 pi, and phi going from 0 to pi, which is the full range of phi and theta. If it's the upper hemisphere, again, theta will go from 0 to 2 pi, and phi will go from 0 to pi over 2. And here, theta is from 0 to 2 pi, and phi, well, phi depends how much ice cream you get. So it's in your interest to have it as large as possible, I guess, although then it becomes more difficult to hold it. So let's just settle on the middle ground, pi over 4. Okay, so that's how you parameterize. This is an example of parameterization. And now, in this case, there is a formula also for, let me erase this, so let's just write the formula, for r, u cross rv. But now we don't have u and v, we have phi and theta. And so r phi cross r theta, in this case, and I'll just write the formula for the magnitude. It's actually what you would expect it to be. It's exactly the formula for the Jacobian, except that you have to set rho equals r in here. So it's r squared times sine phi. You have a question? Right, so the question is about the cone. How do I measure phi? Phi is measured from the z-axis, right? So 0 to pi over 4 would be this kind of range. Yeah, it works? Although I have to say in this picture it looks a little bit less than pi over 4. I don't want to shortchange you. It's ice cream, but this is just an approximate picture. Not the best day to eat ice cream in Berkeley, though. Perhaps earlier in the semester would have been more appropriate. Okay, so that's the formula for this. And let's go back to the double integral. So that's all you need. You need this guy. You need your function where you stick those expressions coming from your parameterization. And then you end up with a simple double integral. So you compute it. What is the interpretation of this? What is the meaning of this? The meaning, just like in the case of type 1 integrals for curves, is that it represents something that has to do with the area or mass. It's something like when you average density over your surface. So the typical example is that this represents mass of, say, aluminum foil in the shape of M, where f, this function f, which appears in that integral, f is the mass density function. Now, it doesn't have to be mass. It could be any quantity which you can measure, which can have a density. For instance, charge. This foil could be charged, but in a complicated way, so that some parts are more charged than others. So you have to integrate, you have to average them out. And so you can have f may be the charge density function, not necessarily mass density function. So then you would be calculating total charge. By the way, if it is mass, you can also talk about the momenta of the mass, which means that you would be multiplying under this integral f by x or y or z, right? So you can also find the center of mass for this membrane, for this surface. So if the question is phrased in the following way, find the charge of a aluminum foil in the shape of such and such surface, if the charge density function is such and such function, then you immediately know that you have to do this integral. Okay? So that's the integral of the first kind, or type 1 integral, over surfaces. And next we go to type 2 integrals. Type 2 integrals are integrals of vector fields. In this case, we're given a vector field f. We're given a vector field. And we're computing this, which is sometimes called surface integral of the vector field, but oftentimes it's also called flux. Flux of f across So the word flux, if you see the word flux, it refers to the integral of the second type. And I explain what it means. It means the rate of flow, for example, of a fluid through this membrane, if F is a velocity vector field. So this integral actually was defined originally as follows. We said that we have to take the dot product of F with the unit normal vector field along M. Then this will be a function, and then we take its integral as a type 1 integral. So this definition already makes clear that we need orientation. We need a choice of n. So just like the integrals of second type, of course, are not really well defined if you just specify vector field and the surface. Integrals of the second type are also not well defined if you just specify vector field and surface. You have to specify orientation on your surface. So it's exactly the same. We need orientation. And orientation should be given to you if you have to solve a problem. The orientation, if you are given a problem where you have to compute the flux of a vector field across a given surface, the problem has to say what is the orientation, or there should be a way to find which orientation is supposed to be. Okay. Now, again, there are two different types of orientation. There are two different orientations. In case the surface is orientable, but of course we'll be dealing with orientable surfaces. I explained to you Möbius strip. Remember, Möbius strip is an example of a surface which is not orientable. But we will be working with orientable surfaces. So an orientable surface will have two different orientations, which will differ by sign. So how do you find out which orientation to use? So let me first of all rewrite this to make it computable as a double integral. So again, I'm assuming that my surface is parameterized in this way by these functions in u and v. Okay, and in this case, this double integral will be written as follows: will be double integral over this domain D, which you have there, and then here you'll have f dot ru cross rv. I mean, in principle, you could try to compute this integral by using this n, and there are different ways. There are different ways to try to find this normal vector. Okay, a unit normal vector. So you could actually apply this formula and then compute this integral as a type 1 integral. You could compute it as a type 1 integral, but I strongly suggest that you use this formula for it. Okay? Because the point is that it's easy. There are many ways to find a normal vector. For instance, we talk about normal vectors for graphs of functions, for example. But what you need to do after this, you have to first of all normalize it. You have to get a normal vector of unit length. You have to normalize it, and then in addition, you'll have to compute this ds, which itself is a rather complicated task, right? You have to compute this ds, which we here compute as the magnitude of ru cross rv. The nice thing about this formula is that this formula is obtained from this formula where instead of n, you take this ru cross rv, which you normalize by dividing by its magnitude. So what happens is that there is some cancellation. This magnitude gets cancelled by the same magnitude in the denominator. So the formula actually simplifies. That's why I think that this formula is nicer. So it's easy to get confused if you use a different type of formula. I mean, you can do it at your own risk if you like. If you know what I mean. But I just think that this is the best way to do it in the framework for the kind of problems that we are dealing with here. Okay. So here's the formula. But how do you see if this is the right answer and not it's negative? You see, so this is a big question. How to see that you get the right orientation in this formula? In other words, you could have a problem, say, where you're asked to use orientation, to compute with respect to the orientation, upward orientation. So let's say you're asked to use upward orientation. How do you know that this formula gives you the integral with the upward orientation and not the downward orientation, for example, right? So first of all, what do we mean by upward orientation? It means that you have to choose n of the form something times I plus something times j, where this doesn't matter, plus something which is positive times k. This is upward. And if I put less than 0 here, it will be downward. So that's the terminology. Upward vector is a vector whose k component or z component is positive, and downward vector is a vector which has a negative z component. Okay. So let's say you're asked to compute the integral over surface, assuming the upward orientation, and you have this formula. And the natural question is, does this formula give me the upward orientation or it gives me a downward orientation? We have to check that, because if it does give me the upward orientation, I will get the right answer. If it gives me downward orientation, then I will get the minus sign. I will get the negative of the right answer. So it means I will get the wrong answer. Right? If I get the wrong answer, it means that I don't get the full score on this problem. Right? So how do you see that? Well, here's an example. Let's look at some special cases where this actually can be computed more explicitly. And the first case is the case when M is part of the graph. So for example, let's look at the case when M is part of the graph of the function g of xy. In this case, we have already computed Rx cross Ry. It is written on this formula. This is Rx cross Ry. So let me just copy this formula here. So in this formula, the coefficient in front of I and coefficient in front of j depends on this function that you have, of which you are, which gives you this graph. Right? So this coefficient depends, but this coefficient is always equal to 1. So this coefficient is 1. So it's positive. And so that means that if you are using this formula for Rx cross Ry, right? If you're using this formula for Rx cross Ry, then you are getting orientation, or you're computing, this formula is computing the integral with respect to the upward orientation. You see, so this is an important point. That a priori, it could be, this gives you a normal vector, not normalized, not unit, but it gives you a normal vector. And by looking at this vector, you can find out with respect to which orientation you're now computing. And then you have to match that with what you're asked to do. In this case, Rx cross Ry, so you have to look more closely at this vector and see what does it look like qualitatively? In this particular case, the simplest information we can infer about this vector is the fact that coefficient in front of t is 1, so it is upward. It's always upward. So now you match, you see, okay, so what am I asked to do? I'm asked to do the double integral, surface integral with respect to the upward orientation. Oh, is my orientation upward? Yes, it is. So this is the right formula. F dot Rs cross Ry is the right formula. Is the right formula. If that for upward orientation. But what if I want to trick you and ask you on the test, ask you to compute the double integral, compute the surface integral with respect to the downward orientation? If you don't pay attention, if you have copied this formula on your cheat sheet, right? And you copied this formula on your cheat sheet, and so you think you're in good shape. You just apply this formula and you get an answer, but you get the wrong answer because you did not pay attention to what was asked. You were asked to compute with respect to downward orientation, but you computed with respect to the upward orientation. Just simply because the formula you are using always gives you upward. But I have the right to ask you to compute with respect to downward orientation. You know, both integrals make sense. It's my right and my prerogative, in fact, to ask you to ask you to compute with respect to any orientation that I like. So in that case, you have to be clever and you have to put a minus sign. So this is the right formula. This is for downward orientation. Because putting this minus sign, you can interpret it as putting a minus sign in front of Rx cross Ry. If I put it in front of Rx cross Ry, I will get plus here, and most important, I get minus 1 here. If I get minus 1 here, I got orientation vector, which is downward. So that matches what I'm asked to do, right? To do the downward orientation. So that's why this is the correct formula. Is this clear? Ask me. Okay, go ahead. Right. I'll give another example in a minute for when it's not upward or downward. Very good. What if the coefficient is 0? So okay, in this case it never happens, right? Because in this case it's just always like this. So here's the next level of trick question, which is that suppose that some RU cross RV, okay, but for some RU and V, and suppose it happens that the component of the k vector is 0, right? In this case, I should not be asking you to compute with respect to upward or downward orientation, because if its k component is 0, it means it's parallel to the xy plane, right? So it's neither upward nor downward. And saying that compute with respect to upward orientation would be misleading, or ambiguous. It will not give you any information because neither of the two vectors is upward or downward, right? So in this case, you actually have to use another way to describe it. Okay. So what are other ways to say? We have to describe in words, you know, the two possibilities. You have to be able to distinguish between them. If the k component is non-zero, you can distinguish between the sign of k, right? You can say positive sign or negative sign. But if it is 0, for example, you can talk about the sign of the coefficient in front of j. Even in this case, here's another trick question I could ask. Instead of saying compute this integral, even in this case when it's part of the graph, instead of saying it's the upward or downward, I could say compute it with respect to the orientation, which is to the left. Okay. So what does it mean? What should you do if you see that? Don't panic. It's if the orientation is described in terms of left-right, it means we are talking about the y coordinate, right? Instead of the z coordinate, which would be k, we're talking about the y coordinate, which would be j, right? So to the left would mean that the coefficient is negative, and to the right would mean that the coefficient in front of j is positive, right? Now, of course, in this case, it's not clear. It depends on the function g. Sometimes just the fact that there's a minus sign here doesn't mean anything because the function could be negative, so then the total sign would be positive, and so on, right? But in the particular example which you are computing, you should be able to see if it's positive or negative over that range. You see? So what I'm saying is, what you are interested in is just a piece of the graph. So you are working with a particular domain D in UV. And you have to see whether over this domain, a certain coefficient is positive or negative, right? That's all it is. And for example, suppose you find that RU cross RV, let me now switch to the more general setting where you actually have coordinates U and V, and it's not necessarily a graph of a function, but some other more general surface. So you could have RU cross RV is equal to some, you know, some A of UV I plus B of UV J plus C of UV K. This is what you will compute by taking these partials and taking the cross product. So you'll get 3 functions, and then you just have to look closely. What do they look like? Well, let's say this is u squared plus v squared. Okay, so then it's not 1, but it's going to be positive. Well, the only point where it will not be positive would be 0, 0. So let's suppose that your domain does not include point 0, 0. So then it's always positive. If you see that, you know that the coefficient in front of j is positive, which means that the orientation vector is pointing to the right, right? Because this is x. Well, of course, when we say that, it's all relative to how we organize our coordinate system. What do we mean by left and right? But there's a way which we can use to, which would be like x goes this way and y goes this way, and this is a z, right? So in this case, to the right means that it's a positive number in front of j. To the left means it's a negative number in front of j. So in this case, it's going to be a vector, not necessarily like this, but maybe like this. So this is to the right. And for the left, this way. Is that clear? There is another way to describe orientation by